In question 2 of this series, where we find the directional derivative of a function, we ended off with question number 2, which asks, find the directional derivative for the function f at xy, which is equal to this expression at the point 0 and 1 in the direction of the point 5 and 2. Notice the difference between this question and the previous. In the previous, they tell us what the vector is, whereas in this question, they don't tell us what the vector is. They tell us that they want the directional derivative from this point to that point. So what we have to do is find the dimensions of this vector. In other words, its horizontal and vertical magnitudes. On an xy plane, we would have something like this. We have a point at 0 and 1, which is up here, and another point 5 and 2, which is up here. And the distance from here to here is 5, and the distance from here to here is 1. So our vector has a magnitude along the horizontal of 5 and 1 for the vertical. At this point, we need to find the unit vector. And to find the unit vector, let's call our vector, this black line, u. And u is defined as 5i plus 1j. The I and the j represent the x and y components. The magnitude is found by taking 5 squared plus 1 squared, square rooting that, and we get the magnitude of u. The magnitude is represented by these double absolutes. So 25 plus 1 is 26. We have the square root of 26 as the magnitude of our vector. Now we take the magnitude and we'll divide 5 and 1 by the square root of 26. So 5 divided by the square root of 26 and 1 divided by the square root of 26. And the reason why these are important, I'm going to call this A and this B, is because in the previous question, we needed A and B to find the directional derivative. And one more adjustment that I'll make with question number 2 compared to question number 1 is I'll use a more traditional way to represent the directional derivative. In other words, its notation. So rather than d sub u, as we had here, I'll write down the gradient, represented by this symbol known as nabla, of our function f at x and y. So I'll use that rather than du. Let's go ahead and show that underneath. So we have the gradient of our function at the point 0 and 1 is equal to, now we need to find the partial derivative with respect to x. Let's go ahead and do that. The partial derivative, f sub x, is equal to, this becomes 2 times 3, x to the power of 2. And over here, that becomes exy squared plus 5y. Multiply 2. The derivative of this term is 1y squared. And the derivative of this term is nothing. It's a constant. So we just found f sub x, and we will evaluate this at 0 and 1 in a moment. Now let's find the partial derivative with respect to y. This is a constant. It becomes a 0. And then we have e to the power of x y squared plus 5y. Let's take the derivative of both of these terms. This becomes 2yx, and this becomes 5. So now we will evaluate both of these functions at 0 and 1. If you evaluate this one at 0 and 1, you should end up with e to the power of 5. And if you evaluate this at 0 and 1, I'm not showing my work, but you can easily confirm using your calculator, you should end up with 5e to the power of 5. So now we will take e to the power of 5 and multiply it by 5 over the square root of 26. And the formula tells us that we take the sum. So now we add 5e to the power of 5 times 1 over the square root of 26. Essentially what we're doing is taking the dot product of e to the power of 5 and 5e to the power of 5 with 5 over the square root of 26, 1 over the square root of 26. That's another way of looking at it. So, multiplying and adding these together, we should end up with the gradient of our function, which is 10e to the power of 5 over the square root of 26. And there you have it. That is how to find the directional derivative of a function.